In this film, we'll describe some valve types and how they are used. In Part 2, we'll cover some details of valve operation, some do's and don'ts, and then something about traps and piping. In generating stations, pipes, valves, and traps are the arteries which interconnect various pieces of equipment. Valves are designed to provide one or more of the three basic functions shown here. Valves are made in such a variety of designs that a brief description of only a few fundamental types will be given in this film. Gate valves get their name from the shape of their wedge-like disc. The disc, or gate, is approximately the full pipe size and fluid flow is straight through. The gate is raised or lowered by turning the hand wheel. The gate valve is used primarily as an on-off device rather than for flow control. When the gate is closed, the wedge seats firmly and acts as a positive seal. A gate valve is inherently tight and imposes minimum fluid friction because of the straight-through design. Gate valves should be operated in the fully closed or wide-open position. The gates and seats erode rapidly in any position except wide open or fully closed. Another gate valve disadvantage? Well, fluid flow does not change evenly with valve stem travel. Most of the change occurs near shutoff at relatively high velocities. For flow rate control, a globe valve may be used. Globe valves have a circular disc which fits on or in a shaped seat. And the disc travels at right angles to the seating plane. Flow through the orifice is usually at a 90-degree angle to system flow, so fluid losses due to high friction may be high. The rate at which fluid flows through the valve is regulated by the disc position. Sealing is accomplished with finely machined edges. Ball valves are another type of fluid control device. Essentially, a ball valve is like the common tapered plug cock or valve, since 1/4 twist will fully open or close the valve. The ball is located between resilient seats, which assure a tight shutoff and permit ease of operation. Fluid friction losses in both plug and ball valves are inherently low, since the valve part is large and flow direction does not change. Are flow regulators. Flow does not seriously unbalance these valves in any position from open to closed. Check valves, or non-return valves, as these names imply, are designed to prevent reversal of flow through a line. Reversal must be promptly and effectively halted, or tanks overflow, rotation equipment overspeeds, and machinery is possibly damaged. All check valves fall into two basic types, piston and disc. Piston types, including ball and stop check valves, have relatively high internal losses because of flow direction change, but they do seal tightly. Some designs depend on a free-riding piston, which may hang up if clogged with dirt or scale after long continuous operation. In other designs, a bleed line back of the piston helps seat the valve by using downstream pressure. Tilting disc check valves, including swing disc and flat types, keep losses low with almost straight-through flow. They close dependably with the slightest flow reversal or even zero flow. But a tight seal is undependable, especially if the valve happens to close against a foreign particle. Now for relief and safety valves. They come in a variety of designs to prevent equipment damage by relieving accidental overpressure. Most are spring-loaded to operate at a set pressure, but weighted levers or a combination of levers and springs may also provide the load. The difference between a safety valve and a relief valve is slight. A safety valve may be used as a relief valve, but a safety valve fulfills a particular requirement for which a relief valve would not be adequate. Safety valves are used for compressible fluids, such as steam and other gases. This compressibility demands rapid overpressure relief. Safety valves have pop seats and plugs which open rapidly on overpressure, relieving at full flow. Relief valves handle non-compressible fluids, such as water and oil. Unlike a safety valve, the relief valve is designed to open only as far as necessary in order to hold the pressure at which it is set. Immediate full flow discharge is not needed, since a very small flow reduces overpressure. So the plug and seat open and close slowly, discharging back to some low pressure point in the system to conserve liquid, 103% of its set pressure. It should close sharply at about 96% of its set pressure. The pressure drop between opening and closing is called blowdown. As a little side information here, a device called a gag is used during hydrostatic testing to hold the safety valve closed while being overpressurized during the test. The gag should never be left on the valve during normal equipment operation. Now, getting back to safety valves, certain conditions may cause safety valve troubles. They are chatter, leaks, simmering, or hang-up. Chattering is usually a metallic hammering sound, and this can take place immediately after popping or just before closing. If chattering takes place immediately after popping, it indicates insufficient steam or excessive back pressure. If chatter takes place just before closing, it indicates inadequate blowdown, which means the adjusting ring is out of position. In either case, chatter must be stopped quickly, or the valve seat will be ruined. Leakage can result from foreign substance, such as metal chips or scale, becoming lodged between the seat and the feather. Leakage may also be due to interference of lifting gear or distortion caused by uneven strain on flange bolts, or because of an imperfect valve body bearing surface. Simmering, the first escape of steam before the pop, must never be as much as the blowdown. A 2 or 3 pound simmer is allowable and indicates a slight irregularity in the seats. Greater simmer may be an indication of incorrect blowdown control. If a valve has popped and blown down an appreciable amount, but will not close tightly, it is an indication of mechanical interference or an excessively low blowdown adjustment. If increase in blowdown does not correct the trouble, the valve should be taken apart and inspected for mechanical defects. When safety valves blow often, they require maintenance to keep steam losses at 3% when reclosing. 3% represents a considerable loss. To reduce safety valve maintenance, an electromatic relief valve is often used. This valve is opened and closed by an electric pressure drop before it will close, in comparison to the 3% minimum in regular safety valves. This lower pressure also conserves steam. There's less steam header variation, too. The control, when on automatic operation, opens the solenoid-operated pilot to relieve steam in B, faster than steam leakage, from A to B. Higher pressure in A then lifts the main valve disc, which opens the valve to atmosphere. At 1% blowdown, the controller, when on automatic operation, closes the solenoid-operated pilot valve. Steam leakage from A to B builds up the pressure in B, thereby forcing the main valve disc down, which closes the valve to the atmosphere. Almost all valves must be physically operated by some type of actuator. Actuation may be electrical, mechanical, hydraulic, or pneumatic. Mechanical actuators include the familiar hand wheel. At high temperatures, where binding could take place and make turning difficult, a pounding arrangement is used. The hand wheel moves freely through a portion of its turn and then hits a lug on a secondary wheel which is fastened to the valve stem. The valve can then be pounded shut for tight closure or pounded open when tightly shut. Chain wheels are useful for valves which cannot be located within easy reach, such as near the ceiling. The operator opens or closes the valve using the chain, which drops within his reach. Manually operated gear heads give the operator a mechanical advantage, permitting one man to operate a valve where 2 men might otherwise be needed. And since the operator will have to take several turns on the hand wheel to produce 1 turn of the valve stem, Portable air motors may be used to operate the hand wheel through a pinion and ring gear arrangement. Remote operation of valves may be provided by electric motors. Remotely operated valves can be used in extremely inaccessible locations. The electric motor may be operated manually using a push button or automatically by electrical interlock with the control system. Solenoid-operated valves are snap-acting and are mostly limited to small sizes. Solenoid valves are popular. One side of the piston feels increased pressure, while the other is reduced or bled off. The force and travel needed to operate the valve is attained by varying cylinder size to agree with the available hydraulic pressure. Pneumatic actuators or diaphragm-operated valves translate an air signal into valve stem motion. Air pressure closes the valve and spring action opens it. In reverse action, the air pressure opens the valve and the spring closes it. The duplex design uses two different air pressures on either side of the diaphragm to provide valve opening force. Okay, now turn to page 18 in your booklet and take the quiz for part 1. See whether you remember what we've just discussed, and when you're finished, restart the machine. Electric motors permit remote operation of valves in either direction. The valve can be located anywhere under remote conditions. For number 2, chattering is usually a metallic hammering sound. This can take place immediately after popping or just before closing. Number 3, valves can be designed to cut the flow on or off, control the flow rate, prevention of flow reversal, and safety of equipment by allowing overpressures to relieve. For number 4, relief valves are for non-compressible fluids, such as water and oil. On the other hand, safety valves are for compressible fluids, such as steam and other gases. Blowdown is the pressure drop between the opening and closing of a safety valve. An electromatic relief valve requires only about 1% pressure drop in comparison to the minimum of 3% in regular safety valves. This results in less steam loss and reduced safety valve maintenance, since constant popping of the safety valve makes it unreliable. This next question is absolutely false. A safety valve is there for safety, and the only time you use a gag is during hydrostatic testing. Well, this wraps up part 1 of valves, traps, and piping, and if you wish to repeat the film, you may, or go on to part 2 with the